This is the classwork today. We have to compare these options. We're not using a building. We're just doing things. We're just well, that will be integrated in a building, but we don't have to model a building now. The idea is that when you are working with your model for the final assignment, you will have to place PV panels on your roof or in the area where the building is placed, and then we will have to analyze that. But the amount of panels, it's up to you and it's up to the project you are working with. Okay, so I'm not giving you for the final assignment, I'm not giving you the amount of panels that you, or the angle. This is something that you have to find out. So we are using Revit, PWatts, and ARCH360. Let's start with Revit. So with Revit, I have opened a file and I have just placed 2 grid lines, 30 feet. Okay, so because we need to measure the area of the panels that we are using. So there is no information about the area, and I don't mind. It can be 30 feet, the distance between 2 grids, or 40 or 50, I don't mind. But we need this number because we need to measure the area of the PVarray that we are using. So if we are working with Revit, we have 2 options, a tilted roof or an open rack. In Revit, we cannot decide whether we have tilted roof or open rack. In PVWatts, we can. Okay, so those are different inputs. In Revit, we don't have the ability to do this. Okay, so this is mounted on the roof or it's an open rack. And there's a difference. We will explain the difference later. But for example, in Revit, we can't use this. In ARCH360, we can't use this option, but in PVWatts, we can. Okay. Anyway, we have different angles. We have 10 plus something and 40 plus something. So around 10 to 20 and 40 to 49. Let's analyze 2 options. So I'm working with this. I am going to the 3D view. If I go to this right option, there are so many levels. I just need the 0 level. I'm going to delete all these default levels. And I just want the 0. Level 1. Okay, there are 2 angles, 10 and 40. Probably there is a family, or you can find a family that it's a PV panel family, but I don't know how it works. So I'm going to generate a roof, okay, and I will pretend that that roof is a PV panel. So I am going to work with architecture roof, but I'm going to use roof by extrusion. Well, before that, I'm going to create a roof, something very thin. Okay, I want to create a roof, work plane. Okay, roof, and I'm going to edit type, and I'm going to duplicate. I'm going to name this roof as PV panel. And I want something very thin, 1 inch. Okay, so 1 inch. And I'm not talking about material. I just want a roof that it's something very thin. Continue. Probably you will have to draw something. Click OK, and now we have this roof. And now you can delete it. And now the system is, or that kind of roof is on the system, because what I want to do on the 3D view, the right elevation, I want to create a roof by extrusion, and I want to select a grid 1 or grid 2, grid 1. And now I'm going to work with the angle. What's the angle? Well, we have this angle or this one. So if I'm working with 10, if this is 180, so that would be 170. Okay, this is the 10. Yes?
Do you mind doing that again?
I will. I have created a roof with 1 inch, and now I am working with roof by extrusion. I have to pick one of the grids, grid 1, and now I have to work with the angle. If we have to orient this to the south, okay, so the angle has to be in this direction so that the south is here. What's that angle? If it's 10 degrees, usually when we are talking about angles, if this is the horizontal and this is the PV panel, if this is the south, for sure, we're talking about this angle. So if this is 10, this angle would be 170. This is what I'm doing now. So I'm going to work with this angle, 170. Go. And then the length of the panel, what's the length of the panel? Interesting question. We can make it 6 feet. Okay, so it's 170 and 6 feet. This is the PV array that we click OK, and now we see that we have something very thin, the 1 inch roof that we have created. We rotate this, and there you go. Okay. So your angle will be 10 or 11, depending on your ID, but it has to be a 6 inch. If we edit profile, this is a 6 inch panel, and the angle, this angle is 10, and that angle is 170. It it's 10. So if you have trouble doing this, you can always select this and now change the angle here. If it has to be 15, you can type 15, and even you can change the length here. Okay, but make sure that the angle is the right one, and the length is 6. Probably we will change the length, but it will be 6 just to start. So we have this, and then on level 1, I want to move this between these two grid lines so that the length is 30 feet. Okay, so we have a PV array that it's the length is 30 feet, and the size of the panel it's 6 feet. Probably we will change it because then we will have to calculate, especially in PV watts, we have to calculate the DC size of the array, and and then we will in F-chart we have to select the right panel. Here we don't have any information about the panel. We just have a roof, and we will calculate the PV potential of that roof. So we have this. Yes.
It's not when we draw for it all on the level 1.
Okay. So this is the PV array, and then there will be another one with 40. I'm going to do just one. You have to do the other one. Okay. But this is 10 degrees. And now, if we want to calculate the PV potential or the PV performance of this roof, if it's a PV panel, so that's what we are going to do. You have to go to Analyze, and remember that you need this solar icon here. So make sure that you all have this, because without this, we can run the energy analysis or we can run the solar analysis. Okay, so I installed the plugin in all the computers. But if you're working with your laptop, you have to install this plugin, and this solar icon has to show up there. Okay, so we are going to click this solar, and here you see that we have different options. So the study type is solar energy, annual PV. Well, I would say custom, because probably we're doing something different. Here we have different options. We have to use sun settings. That's important. We have to use sun settings, apply. The location before that, I have to change in manage. I have to change location, and we are going to work in Keene, New Hampshire. So now I go back to analyze, solar. Now the weather data, it will be in Keene, New Hampshire. The analysis period, we can use full annual, but I'm going to use sun settings because I want sun settings. And here we have information about the building area, the building energy, the electricity cost, the panel type. So here we can select what kind of panel we have. But okay, so don't do anything yet. So we will select this apply, and that's it. Now the surface, we can select all roof or all mass surfaces, but I'm going to select my surface. So you can click on that arrow. And well, by default, we only have this, so that's the only surface that we have to select. But remember that we have to click finish here. If we don't click finish, we cannot do anything else. We cannot update. Yes, we have to click finish. And here we can do this. We have the cumulative insulation. Okay, cumulative, it's good. Finish. And the style, source analysis default. Okay, I want to select this solar analysis. It's annual. Let's select the solar analysis default. And see what happens. There will be cumulative insulation, kilowatt hours per square meter. You can change the units here. Let's select kilowatt hours because this is what we are going to use. Okay, and let's click update. Okay, so this is the solar radiation that we have. But what is this value? It's kilowatt hour per square meter. How many square meter? If we have the area of this PV array, we can do that. If you don't like this, we can use BTU hours per square feet. Okay, but eventually we need the kilowatt hours. Here we are not doing anything about PV panels. What we are doing is just analyzing the amount of solar radiation that we have, taking into account the sun settings. What are the sun settings? We don't know. We have to open this and open the sun settings. And we have a yearly, because this is from January the 1st up to December the 21st. Okay, so by default, the sun settings consider a year. So that would be the energy that, again, so this is the energy that we are receiving on this roof. It's not even a PV panel. That's the energy that we are receiving on our roof through the year. So we are receiving 1,319 kilowatt hours per square meter. So that this is not the PV performance, but this is something that we can compare, for example, with PV watts. So if we open PV watts now, if we place this in Keene, New Hampshire, we go. Okay, what can we, here we have information about the system, about the panel itself. We haven't selected any panel in Revit. So just to compare this information to the information that we have in PVWatts, what do we have to do? We don't have to touch anything about this. We have the tilt, we have changed that. So you have to type here the angle that you have selected here, and the azimuth is south. In our Revit file, the panel is south oriented. Okay, so in PVWatts, this would be 180 because it's south oriented, and we have only changed the angle here. If we go back, or if we move, we move on, not go back. So this is the solar radiation in kilowatt hours per square meter per day. You see this value? And we have the annual one. So this is 4.25. We are in Keene, New Hampshire. We have a PV array. We have the right angle. And here we have information about the energy per square meters per day. And here we have, I will update. Well, it's energy per square meter. Here we have the final result. So we have 1,319 kilowatt hours per square meter. The total, it's going to be 22. Well, but I'm going to use this one. Okay, so I will write down this value. $1,319 kilowatt hour per square meter. Okay, what's the result in PVWatts? In PVWatts, we have a 4.25 kilowatt hour per square meter in day. How many days? If we are in Revit, we have done a yearly analysis, so we have to multiply this by 365. Is it the same value? Let's find out. 365 times 4.25. 1,551. That would be kilowatt hour per square meter. What? We don't know. We don't know. So which one is correct? I am conservative, so I tend to think to, okay, if I have two values, so I will take the lowest one to be pessimistic. But this is the kind of things that we have to analyze. I don't mind if I only have Revit, I will go for this value. If I only have PVWatts available, I will go for this value. Is there a huge difference? 170 kind of kilowatt hours per year. It's not a huge difference, okay? But there's a difference. So we have here the two different softwares. We have done exactly the same, and they give us two different results. And this is the solar radiation. We are not talking about the energy. So we have not taken into account the quality of the PV panel or the performance of the PV panel. This is probably they are using the same database because everybody used the DOE, the Department of Energy database. So probably the database that they have is the same, but I don't know, maybe the average is different, or maybe they have considered, because if we are placing this at Keene, New Hampshire, we have the average of solar radiation over, I don't know, when they started measuring solar radiation in Keene, New Hampshire, maybe in at the beginning of the 20th century. I don't know how many years, but depending on this average, these results are different. Okay, so now we are analyzing the difference between two different software, and it's the same. We have just placed, and we are doing this per square meter. Okay, so we are not taking into account the area. It's just per square meter, and there's a difference between these two values. Keep that in mind. So it's not a big deal, but we have a difference in the solar radiation. So this is the objective data. So this is not something that depends on the performance of the PV panels, on the system losses, on. So if just with the objective data, the solar radiation using the same database, and if there are two different results, okay, so it's not important, but make sure that we know this. We can refine the analysis, yes, because here we haven't included anything about the PV array. So we are going to work with this. We're going to use the, instead of custom, we're going to use the solar energy PV. Okay. What do we have here? If we select this, we do have information about the panel. Okay. Here we have the building area. We are not designing a building. Here we have information about the building energy. So we can include the kilowatt hours per square meter per year that we have in our building. But before that, we need to run a simulation. Okay, so if we're working with Revit, first we run the simulation. We have done this before. We have a number about the kilowatt hours per square meter per year. And this is the energy that we have to introduce here. The electricity cost. Yeah, so Revit has economic parameters. We don't have economic parameters in PV watts that I know of. Also, here we have, yeah, we do have economic parameters, but I don't know if we can fix it. I don't know, but we do have economic parameters in ARCH. Okay, we're not talking about economics, basically because first, I don't understand, and second, things are changing now. When I was running this analysis like 5 or 7 years ago, when we had to define the inflation, it was only around 2%. Because the inflation was steady, kind of, but now the inflation is, what's the inflation rate now? 7, 8, what will be next week? We don't know. Okay, so we're not going to run this economic analysis. The electricity cost, we can find out. We can find out the price of the kilowatt hour of electricity in KIN, or you can go over your electricity bill and you can find out this price. But now the market is changing. So why not? And here we have the panel. Okay, so here we have 16%, whatever, and we have, okay, this is the efficiency. We have efficiency from 16 to 20. 20 is always better than 16. Okay, but we have some information about the panel efficiency. And here those are information about the payback filter. This analysis is for 50-year payback. I think by default in ARCH is a 20-year analysis. Again, this is about economics, and this is the analysis grid. This is the number of points that this is analyzing. This is relevant when we have abstractions, we have shadows or shades, because depending on how many points we analyze, we can make a mistake or not. Okay, if we have a PV array that is like this, and we have a tree or whatever, and we have this part that is in shape, how many points are we analyzing? If we only analyze 1 point here, we don't take into account the shadows that we can have here. If we divide this into a grid and we analyze different points, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so probably only this point is giving us information about the shape. Okay, so we don't have any sum here because we have a shape there. And the more points we analyze, the more accurate the analysis will be. Okay, because if we increase the number of this grid, there will be a lot of points with shape here, and a lot of points without shape. In this case, we don't have any shape, so this is not relevant. I would use the, or we can go to find, but without shape, the difference is not relevant. Okay, but let's do this. Let's apply. So now we have analyzed annual PV. We have analyzed the surface. We have to select the same surface that we have selected here. Okay, it's the same, finish. And here, let's select the PV energy. Okay, so cumulative insulation is the energy that it's heating on that roof. But now we don't want this. We don't want the solar energy. We want the PV energy. So now we can select the PV energy. And this is the solar analysis annual PV energy. It's in kilowatts per square meter. So let's update. Okay. So what we have here is a total of, we have 3,000. Okay, so we have already compared this from PV watts and Revit. So in Revit, this is 3,528 kilowatt hour per year. Okay, and the area of this PV panel area, this is what we have selected. It's 17 per meter. That's the area. If we change the units, here we will have 180 square feet. Makes sense. It was 6 times 30, it's 180. Okay. So let's stick to square meters. So this is the result. This is the area of the PV array. This is the energy performance. And remember that we have selected an efficiency. Efficiency is 16%. This is the efficiency of the PV panel. Okay, so those are the inputs, and this is the output that we have. So this is the total energy that we can generate in 1 year. What is the result in PV watts? So in PV watts, we do have this information. We have the AC energy per year. So in this case, we have 4,723 kilowatt hour per year. Okay, so this is PV watts. Here we have 3,500 and here we have 4,700. There is a difference between these. So what have we got? What are the inputs? Here we do need to know the quality of the panel that we are using. So this is the DC system size. Yes, so that's relevant now. Okay, so we have generated this, but with this DC system size in kilowatts, it's 4. In Revit, the input is the area. It's 17 square meters or 180 square feet. So this is 180 square feet. Okay, and the efficiency is 16%. That is the DC size it's 4 kilowatts. Okay, so this is the input in Revit, and this is the output. This is the input in PV watts, and this is the output. Is this 17 or a square meter or 180 square feet of PV panels with this efficiency? Probably not, because it would be something outstanding, because I haven't calculated it. So now we have to change this number. Here we have something about the performance. Okay, so this is a standard. I told you that there's standard quality, premium quality, or thin film. We're using standard. What does it mean? In terms of Revit, is 16% standard. I have selected the lowest one. It can be 16, 18, or 20, the efficiency. I have selected the lowest. Okay. But there is no way. We either ask the Revit developers what they have used or why they have used this, or we ask PV watts developers what the standard means. We don't know. Okay. And then we have here the fixed open rack or the fixed roof mount. In Revit, we don't have this information. Probably open racks, it would be slightly better than the other one, than the roof mounted array. Okay, but we don't have this information in Revit either. But we do have information about this size. And where do we get this information? I have uploaded place. Okay, this is the glass. This is just a double glazing, triple glazing. But I have uploaded this PV solar brochure that I took from my favorite website, Alibaba. And okay, so this is what we have to look at now. Here we have information about the panels. We have this panel, one, we have this is a different one, two, and this is a different one. We have 3 panels. You can decide whatever you feel like, okay? The first, the second, or the third. But we need to understand now the characteristics or the specifications of these panels. Here we have dimensions, okay? So this, it's 1,640 millimeters by 992 millimeters. So this is around 5 feet by 3 feet, kind of. Dimensions of this are different. This is smaller, it's 1,200, and this is 1,600. Okay, so this is smaller, and this one is 1,400. Okay, so apparently this is the biggest one. If this is the biggest one, then we have to look at the maximum power. The maximum power of this panel is 185 watts. What's the maximum power of this panel? Well, there are 2 categories here. Because we have 2 dimensions. Yes, so you see that this is 1,500 and this one is 1,200. Okay, yeah, we can see here that there are 2 different dimensions. So the small one is 95, the big one is 190. Okay, and then this one is 140 watts. Okay, so we have 3 panels. The first one is 140, but with these dimensions. The second one, it can be 95 or 190 with these dimensions or these dimensions. And the other one is 185 with this. So which one would you select?
The one closest to what we drew in Revit.
The one?
The one closest to what we drew in Revit size-wise.
The one size-wise, and which is this? What's the, well, in Revit we haven't used a panel. We have this rectangle, and that rectangle was 6 feet. Okay, so what is 6 feet in millimeters? 2 millimeter converter. So if we have 6 feet, this is 1800. Okay, so it's slightly bigger than the biggest panel that we have here. Okay, so according to your decision, I don't mean that it's the wrong one, but according to your decision, we will select this one, because this one is 1600, this one is 1500, and that one was 1400. Okay, so we would select the first one. Okay, fine. I don't. But what we have here is the total dimension of this panel. Okay, so imagine that we are selecting this one. Are we done with this? No. Life is complicated. Look at this. Here we have electrical characteristics, NOCT. And for the other panels, we have electrical characteristics, STC. Can somebody tell me the difference between NOCT and STC? That's very important. And Revit doesn't, we can't include this kind of information in Revit. NOCT PV panels. Stands for nominal operating cell temperature. Okay, and what about STC? It's the standard test conditions. Okay, so the STC is an industry-wide standard to indicate the performance of PV modules. Both are standards to indicate the performance of PV modules, but the STC is the standard test conditions. The cell temperature is 25 Celsius. 25 Celsius, it's around, its comfort temperature is around 72, 73 Fahrenheit. The irradiance, it's 1000 watts per square meter. And this is the wind speed. Okay, so within these standard test conditions, we have three parameters: the outdoor temperature, the solar irradiance, and the wind speed or the wind velocity. Well, standard test conditions usually are the best conditions for a PV panel, because the PV panel has an efficiency of 16%, 18%, 20%, or whatever, but under these conditions. And those conditions are optimum, okay? If the temperature is different than 25 Celsius, Celsius to Fahrenheit, if this is 25, it's 77, slightly well. Okay, so if the temperature is different than 25 Celsius or 77 Fahrenheit, the performance of the PV panel decreases. Okay, so we can have this 16% of efficiency. Probably this is under the standard test conditions. When do we have 77 Fahrenheit? In Kin, probably a couple of months. But 77 Fahrenheit, this is the optimum. But if it increases, then the performance drops. So sometimes if we are looking at the outputs of a PVarray in summer, it can be lower than some days in winter, because in summer, when it's very hot and the sun is heating on the panel for a long time, probably the temperature of the panel increases. It's not 77, it can be 100 or 120 Fahrenheit, and then the performance of the PV cell drops a lot. And we say, it's summer, it's a sunny day. How comes? Why the performance today is worse than in winter? Because it's too it's too hot. Okay. What about the other condition? What about the 1000 watts per square meter? So this is the solar irradiance when we have in a day without any clouds at the best moment. Okay, so when we have a cloud, this is the maximum solar radiation that we can have on the Earth surface. Okay, so we are testing this with the optimum temperature, with the best solar radiation, and probably the wind speed is very low. Okay, so when do we have these conditions? Probably 2 or 3 seconds per year. So what when we have this efficiency under standard test conditions, that means that we will be producing this, I don't know, a few seconds a year, because it's very likely that when the temperature is the optimum temperature, we have a cloudy day, or when the solar radiation is the best one, the temperature is either too hot or too cold. Okay, so we are simulating something, but we are simulating something under, so the reality will be worse. You understand that? Okay, so we have this simulation, but we have these inputs, and these inputs are under these conditions. To solve this, we have the NOCT, the normal operating cell temperature. So the normal operating cell temperature, it's another test. Depending on where we are, if we inform the PV provider about, this is something that probably you cannot do in Alibaba, but if you have a good PV provider, you can, okay, I'm going to place this in Keene, New Hampshire. Keene, New Hampshire, yes. What's the average temperature in Keene, New Hampshire in summer, winter, whatever? And they can test this panel and this under this operating cell temperature. So that information will be in our brochure here. You see, this is the maximum power as at STC. 95 for the small panel, 190 for the big one. This one is tested under nominal operating cell conditions. And what is that temperature? This temperature, it's 45 plus minus 2. Okay, so it can be from 43 to 47. So what they are telling us that is that this panel, if the temperature ranges from 43 to 47, it produces 185 watts. Okay. So based on that, what do we use? Well, this is what we have. We have different panels. We have different information. We have different test conditions. I usually trust the NOCT. So if we have this information, I would use this value. Sometimes we don't have this information because they have the PV manufacturers, they test their panels and they have to give us these specifications. But probably the mandatory test is the STC. So most of the panels, the information that we have is the STC. Okay, so we have maximum power at STC, and this one, it's STC. In this one, we have NOCT conditions. But when we have this, what is the nominal operating cell temperature? They have to let us know what the temperature is, because it can be different. Okay, so they have tested their panel at this temperature. They think, okay, in summer, the temperature will be something like that. So let's give this information because in winter, if we don't have enough hours of sun, if we have snow or most of days are cloudy, we expect that the system will be working well in summer. Okay, so let's test this system under summer conditions. And in summer, we can have 45, it's quite hot. It's 113 Fahrenheit. Okay. So these are the inputs. I'm sorry, but this is what we have. It's complicated. Yes, it is. I wish it were easier, but it's not. So what do we have to do now? With all this information, we have to analyze the DC system size. Okay, so Emily, you have selected this one. Okay, under, well, this is the value that we have, 180 watts, 185. So the PV production is 185 watts. For this panel, what is the area of this panel? The area of the panel is 1640 times 992, no, 949. Millimeters. Okay. So let's calculate the area of one panel. The area of one panel is 1.64 times 0.949. So it's 1.5. 1.55 square meters. What have we done in Revit? In Revit, we have built a PVarray of 17 square meters. So how many panels do we have? It's 17 square meters divided by 1.55. Okay, so we have 10.96. We have 11 panels. Is it clear? Okay, so now with this, we have 11 panels. Each panel is 185 watts. So this is the DC system size. So it's 11 panels times 185. 11 times 185. So this is 2035 watts. So what is the 2.035? It's 2000 watts. It's 2 kilowatts. So this is the DC system size. Now, is this standard? Is this premium? Is this fixed open rack? We have the system losses. We don't know, but let's calculate this, see what happens. Okay, so now the AC energy is 2. This the DC size was 4. If the DC size now is 2.035, now the performance is the total energy is 2,401 kilowatt hours per year. Now it's lower than the Revit performance. Why? Probably because Revit is taking into account standard text conditions that are better than the nominal operating cell conditions. Okay, but we don't know because Revit doesn't give us any information about this. The only thing we can do in Revit is I can increase or decrease the efficiency, but that was the lowest, okay? So we have analyzed these two. Okay, so here we have two different analyses. We have the Revit. I'm doing this in Revit. So I will come here. If this is the analysis, this is the angle I have selected, and I would place here the Revit results. If I update. Okay, I can take a screenshot of this. So this is the Revit analysis. I have 17 square meters of PV panel area. And this is the yearly performance or the yearly output of this. What is the PV watts? The PV watts analysis will be this one. Go on. Okay, so this is the PV watts output. But I think here we need to give more information, because here we know that we have selected, we can go to this page and we can copy information about the panel. Okay, so here we have the dimensions of the panel, and here we have the performance of this panel. So we can paste it here. Okay, with this specific panel, this is the output that we have in PV watts. And we have selected 11 panels. Times 185 watts. So the DC size was 2.035 kilowatts. Okay, so you have to give me this information, because otherwise I don't know if it's right or wrong. Okay, so this is the output in PV watts. Yeah, I can trust you, but you have to give me how many panels you have placed, and what panel you have chosen, and the DC size that you have selected in PV watts. Okay, so this is the Revit output. This is the, well, in Revit, we have the information here. It's 17 square meters, and this is the yearly production. We have the production of in kilowatt per square meter. Yeah, so all the information we need is here. But with the PV watts, in PV watt, we need to select the panel, and then we need to select the DC size as an input. And then we have this output, and we are comparing the annual performance. Okay, so we are comparing this value, in this case is 2000, and in this case would be 3500, and this is 2400. Okay, so there's a third analysis, which is the F chart analysis. You have to do the same now with an open rack with a 40-degree angle. Okay, so you have done this with 10, now you have to do the same with 40. We're going to work with the PV F chart. Here you have to use utility interface and flat array with different angles. The different angles are 10 plus X and 40 plus Y. Okay, so you have to use the same angles that you have used for the other one. We're going to do this one. We're going to do this with 10 degrees. Okay, so we have to open, you have to go to PC, local disk, and there should be like a PV FC demo. Okay, so we have to open this folder. And then we have to open this file, or this. Yep. Okay. So here in F chart, we always have at the beginning we have two windows. We have something about the system and something about the economic parameters. That's very good if we really know something about economics. That's really good because it gives us an idea whether the investment is worthy or not. Okay, so I'm not going to close this, but again, we need to know all these elements, the rate, the mortgage. So there are a lot of things here that probably we don't know. But I'll show you the final economic analysis because it's very good. And here, okay, so let's go to preferences. We have system international units or English units. We are working with international units here. Okay, so let's select international units in preferences, then the system. We have the utility interface, we have battery storage or standalone. The utility interface is a system that is connected to the grid. Okay, so that's why I, in this, use utility interface. We're not using batteries. Okay, so in system, we have battery and standalone. I don't know. Well, the difference is that the standalone, you only use batteries. In this battery storage, you can use batteries, but at the same time, you're connected to the grid. Anyway, to make things simple, we're going to use the utility interface. We have the PV array. If we have an excess of energy, we sell it to the grid. If we need electricity, we buy that electricity from the grid. Okay, we don't have any batteries, so let's use the simple one. And then for the flat plate array or the CPC, this is a concentration. Select the flat plate, and here I have the here. Okay, this is the difference between the flat plate. This is the flat plate, and this is the compound parabolic concentrator. We have PV panels like this, but probably those are more efficient, but they are more difficult to integrate in buildings. So we have this in solar plants. We can use this one in buildings, integrating this in buildings. I don't know, I have never seen that in my life, but maybe there's an option. But this is the 90% of the panels that we place in buildings are flat array. Okay. Do we have information here about the efficiency, about the whether is it crystalline, thin film? We don't. Okay, so we only have these two options: the flat plate or the CPC, the compound parabolic concentrator. Okay. So let's select in system, utility interface, and flat plate array. Okay, we have to select here the northeast. Here we can select king. We select the northeast. So all the systems have some limitations. But here we have the cell temperature at NOCT conditions. Okay, that's good news, because if you remember, we have this information. So what's the normal operating cell temperature? It's 45, it can be from 43 to 47. Okay, so we can type here 45, because we know this. Here it's 44, but we can say 45. So at least we know that the information that we are typing here matches with the information that we have from the PV panel. You need more time, yes?
I don't have utility interface on my system.
Okay, so after these few minutes of tension, I resume the class, and we have to work with the F chart, PDF chart. I'll do it again. References, we are working with units. System, we are using the utility interface. That means that we only have PV panels and we have grid connection. We don't have any batteries. The weather, you can select weather, or you can just, data location is the northeast. Okay, so you can do it either here or there. And then we have run plot. Don't do it yet, because in PV watts, we have to do something that we don't have in other softwares, which is the load. Okay, so here we can change view load, and we can be as thorough as we want. Okay, so we have here the ability to include a lot of information. That's good, but that means that first we need to get this information from somewhere. What is this? What's the load? You see that here we have January, February, March, April, May, June, July. Okay, so we have all the months here, and then we can do it hour by hour. So this is from 0 to 1, from 1 to 2, from 2 to 3. So we can do this 24 times. That's great. The bad news is that, well, we have to type it. Okay, so there is no way to import those values. So we have to calculate those values somewhere, and then we have to put it there. And what is this information? We can go on a monthly basis, hour by hour, including the load, the electric load that we need. For example, if we are sleeping from 0 to 5 p.m., okay, so that's perfect, because this is 0. And then if you go to bed at 11, so this is 0. Is it 0, the load? That means that in January, we are working in June. Well, let's work in January. So let's start in January. So this is 0, 0, 0, and 0. And then at 11, I go. So that means that I turn off every single electric device that I have in my house. Do you do that when you go to bed? No. If you don't, what do you leave on? Imagine that your computer is on. If your computer is on and the computer is consuming 200 watts and it's on for 4 hours, then you would have to type here 200. Why? Because you have left your computer on. Is the fridge on? Yes. What's the electric consumption of your fridge? Is your light bulb outside the house on, just in case. We need to know this data and we need to change it. What about if we, from 4 to 5, imagine that you wake up at 5 or at 4 a.m. and you start doing whatever you do, and then you turn on whatever, the heater, because you have you take a shower, then the hair dryer, whatever. So now what do you do from 4 to 5? Do you consume 1,000 watts? Okay, so let's see that 1,000 watts. Then I turn the heating system on and it's electric. Okay, so and it consumes like 5,000 watts. Okay, so I can say 5,000, 5,000. And then at 8, I leave because I go to my office and then I leave something on, whatever. And then at 6 p.m., I go back home and I consume 5,000 watts. And then 5,000 and 5,000. Okay, so we can be very specific, but again, we need to know what we're doing. We need to know all our appliances, and we need to know the energy consumption of our systems hour by hour. But this is, if we want to run the economic analysis, and we want to run the economic analysis, this is something that we have to do, because if we have selected this utility interface, that means, and this is something that we have to understand. We have a chart here, and well, we can do this on a monthly basis. We are working in January, and we're working one day. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18. Okay, so we have 24 hours. So I'm going to write in green the consumption. And in blue, the production. So according to this, if this is 1,000, 2,000, 3,000, 4,000, and 5,000. According to this, 1, 2, 3, 4, I consume 200 watts. Okay, so this is 1, 2, 3, and 4. This is 200 watts. Then at 5 and 6, I consume 1,000. So this is 1,000 and 1,000. Then after that, 6 and 7, I'm consuming 5,000. 5,000. Then I leave home and I have 100. So if I'm not home, I'm consuming whatever. And then there's a moment I get home again at 6 p.m. So at 6 p.m. I have 5,000 again. And then at 7 I have 5,000. And at 8, 9. Okay, so this is my consumption pattern. This is what I do. I go to bed when I'm sleeping. I don't consume anything, or maybe there's something on, but it's nothing. So the bulk of the energy is when I turn my heating system on, and it happens at the beginning of the day, and then when I come home, because I'm not home here. Okay. So this is the consumption. What is the production? The production, do I produce anything at midnight? No. At 1 a.m.? No. 2? No. So this is 0. When do I start producing something? Probably at 8 p.m. So the consumption curve will be something like this. Okay. What's happening? When I am consuming energy, which is early in the morning, probably the sun is not there yet, or late in the evening when I arrive home, this is my consumption pattern. And this is the PV production, because I don't produce anything when there is no sun. So I produce at noon, probably will be the peak of my production. So this is energy that we have to buy from the grid. Right. And this is energy that I have to sell, because I'm not consuming this energy. Okay, so that's why if we want to be a zero energy it would be better consuming the energy at the same time than producing energy. If I don't have batteries, I can't do that. If I have batteries, probably I could store all this energy that I'm producing here, and then I can use it afterwards. But I need batteries. If I don't have batteries, I either get a good deal or agreement with the electric company. And this is politics, believe me. In a fair world, you would say, okay, so this is the electric company. You produce a kilowatt hour, and then you produce kilowatt hours here, and then you need kilowatt hour there. So if you can sell the same amount of kilowatt hours that you have to buy, you're break even. Well, if this is not a fair world, because the companies invent, oh, this is the valley, this is the peak time, this is valley, and the price of energy is different at different times. Usually the highest price of energy is here and here, because they are smart. They know that when people are consuming, because they have all our data there. They know when we are at home, they know when we leave, they know what we do, they know the energy that we consume on a daily basis. And then they analyze this market and they say, okay, so when do people need energy? Especially at the beginning of the day and at the end of the day. Let's make this the peak hour in terms of energy price. Usually the energy here, it's quite cheap, but the energy here, it's quite expensive. I'm talking about Spain right now. Okay, so this is what they do. In Spain, understanding the electricity bill, it's almost impossible. But this is the spirit of what they are doing. They analyze the habits of people and they say, okay, so if this is what you do, so I'm going to charge you more here. And if you want to sell me energy at this time, the price of the energy now, it's lower than the price of the energy here. So this is what they do. They are mean, they are corrupted, they are terrible. Yes, they are. And they have agreements with the government. There are conspiracy theories. But anyway, we are here to analyze objective data. And the objective data is the energy that we consume and the energy that we produce. All of these, the difference between the price of the energy at this time, the price of the energy at that time, that depends on politics, and we can't control that. But we can control the production and the consumption. So if we change our habits and we work at night and we consume energy, we're at home in central hours of the day, then we can adapt our consumption to the production. And if we do this, we don't need deals with the electric company, or we can install batteries, so we can keep all this energy that we are generating when we are not home, and then we are using this energy when we are home. But again, it comes at a price. It's expensive, and then we need a huge room to install all the batteries, and the technology is complicated, and we have sometimes it doesn't work. But basically, this is what we are doing. Okay. So with this software, we have the ability to control this, but we need to know the habits. My habits, what I do, or if imagine that this is not a single family house, this is a company. In this building, it's the other way around. The maximum consumption will be here. And we don't have any consumption over the night, but here, when all the classes are on or are taking place, we have the maximum consumption, and we do have the maximum production. Okay, fine. But every building is different, and even every family or every person is different. So we need to know what we are doing, and as here we can. And do we do the same in winter or in summer? Do we have a different schedule in winter or in summer? We can be very precise. So you see that we can do it on a monthly basis, every single hour of the day. But first, we need to analyze the habits of the family or the building or whatever. So let's do this, okay? And let's see the outcome, okay? So we have the city, the northeast, the cell temperature, it's 45, the array efficiency. Okay, the array efficiency, here it was 16. By default, here we have 10.1, it's 10% efficiency. Can we change it? Can we make it 16? Yes, we can. The array reference temperature, that's what is this? If we match this temperature to the NOCT temperature that was 45, that would be optimum. But this reference temperature is the average of the year. Okay, so what's the temperature in January, February? I don't know. So let's leave 28. 28 Celsius is is 82 Fahrenheit. Can that be the average? It's not the outdoor air average. It's the average of the cell. When the cell receives the sun, it heats up. Yeah, so it might make sense. Okay, so let's leave 28. Then the array temperature coefficient. I don't know what this is, so don't change it. The tracking efficiency, power conditioning efficiency, the standard deviation load. Okay, those are things that don't touch them because we don't know what they mean. But usually it's it's between 88 and 90%. Well, that's those are common values. And what is the array area? It's the number of panels times the panel area. We know that because we have calculated that in Revit. So this should be 17 square meters. What's the array slope? We can change here. The array slope is 10 degrees or 12 or 15 or whatever. And the azimuth, it's south oriented, so it's 0. Okay. So now we can calculate, run, calculate, and this is what we get. This is the economic analysis, and if we were studying this, you can click on cash flow, and this is very useful. You see, when we have negative numbers, that means that we have paid an investment, we have paid some money upfront, and then we have mortgage, and then we have an interest, so we are paying interest. So when the figures turns from negative to positive, at this point, we start making money. Okay, so we spent like 7 years returning our investment, and as of the 8th year, we start making money with that investment. I have done this randomly, so it's very good. Usually when we do it the right way, the return of investment is around, it's more than 10 years. If it's less than 10 years, that business is quite good, but I've done it randomly. So I haven't changed the interest rate, the price of energy, the inflation, so I haven't done anything. But I think looking at this, it's very intuitive because at this moment, the return of investment is positive. So it takes 7 years to start making money out of that business. Okay, so that would be a good investment. Unfortunately, I can't rely because I haven't changed any of the parameters. And this is information. Here we have the F. F is the amount of the percentage of energy that I'm generating. So in January, I'm just generating only 2.8%. In June, I'm generating 68.7. But again, that depends on the load. I haven't changed all the loads. I have done this only for January. Okay, so that's why for January, the result is very low because the other, I haven't changed other months. Okay, so this F is the percentage of energy that I'm covering with my PVarray. And this is interesting because it's the difference between the energy I sell and the energy I have to buy. Okay. So if the balance between the energy that I sell and the energy that I buy is positive, I think we are doing something better because the deal with the electric company will be better. Okay. And what's the total load? That will be, well, basically, this is what we have to understand now. We have the percentage, we have the energy that we sell, and the energy that we buy. Do we have, oh yeah, and this solar, this is the energy that we, this is the energy, this is the energy that I'm receiving, and this is the energy efficiency. Okay, so the energy production would be this column times this efficiency. So that would be the energy production. So if I want to compare the total output, so this 3,500 or this 2,400, I would have to multiply 900 times the efficiency, 1,000 times the efficiency, and then add everything up and see what happens. I don't have this value there. Let me do this.
I have the yearly average on mine. Maybe you just scroll down and that one.
Oh, the yearly average. Okay, good. Okay, so this is the yearly average. So let me check this. 2,000, it's 22,774 times, and the efficiency is 13%. It's times 0.13. Okay, so the yearly production is 2,906. So that's PV watts. That's Revit. And the PV chart is 2,960 kilowatt hour per year. Well, it's like the average between this one and that one. Okay, so we have tested the same array under 3 different softwares. And we have 3,500, 2,900, and 2,400. So we can say that between 2,500 and 3,500, that will be the expected outcome of our PVarray. So what's the result? What's the final? I don't know why I can't. Okay, we can do this. So that will be the final output of the PV watts, and the total energy the yearly energy will be this value, the total 22,774 times the efficiency 0.13, and that is 2,960 kilowatt hour per year. Okay. So here we have the Revit analysis, 3,500. The PV watts, 2,400. With this panel, the yearly production is this. What were the inputs? We have the area. It's 17 square meters. I think I could select the efficiency. Okay, the efficiency is 16%. It's 16%. What are other outputs? Well, the other one is the array slope, and that's it. Well, we ran out of time, but that would be the final result of this exercise, comparing 3 different software, but we need to understand the inputs, and then we need to understand the outputs of this. Okay.